Okay.
Let me just start the recording, just in case our stream fails like last time. All right, I'm happy to present Misha Kornev for, I guess, the final time in this series, who will tell us about model independence for infinity cosmoi. Thank you.
Yeah, thank you. So I would like to talk about representable infinity categories and model independence. So in the previous talk, we discussed some stuff with the comma categories, and now we establish that these comma categories is useful for the purpose of model independence. So now recall what does it mean in infinity comma infinity category. So suppose that we have two morphisms in infinity cosmos K, say, and then we can form this pullback diagram. So recall that A2 means that it is a arrow category. So 2 stands for the nerve of walking arrow, and we have the following diagram. And the top horizontal map, this one, corresponds to the following 2-cell. So and this correspondence is via the following whiskering. So we can take this comma object and take the composition with the natural 2-cell between these arrows, and then we will have this 2-cell. So this 2-cell is called the comma cone of this comma infinity category G. So sometimes I will use this this symbol, or in some cases I will use the following notation like this. Like this. So I'll write from A, from F to G. So comma object is the natural natural thing, natural object for the notion of object home object. So home object is precisely the comma infinity category. Okay. So and this I recall. What does it mean that this 2-cell is the canonical 2-cell? It means that we have this isomorphism. So the definition of this tensor cotensor product such that this holds. Okay. So the next definition, we can take an identity morphism in this case, and we will denote as FA, or home from F to A, the case when the morphism G is replaced by the identity morphism on A. So this is just a particular case, so this construction of the first construction. And in this case, we will have the following two cell. So this two cell reduces to the triangle, and we can write down something like that, and but of course we can reduce it, and we get a triangle. So and the same notion for the so and we will call this two cell as or this comma object, this comma object as a left representation as a comma infinity category. So if in some cases we will if in some cases we have the equality that some comma object between F and G equals this one with identity one, then we will say that we have a left or right representation as a comma infinity category, and this object, this map we will call this map will be called representative object. And so the following week universal properties. We know that in general case we have a bijection between these square diagrams and these fiber isomorphism classes of these diagrams. So fiber isomorphisms, this notion means that we have an equivalence modular these diagrams. So if we identify such diagrams for which we have isomorphism here, which fits into this commutative diagram. So we have this bijection, and in our case we have the following bijection. So this triangle corresponds to this square diagram modular fiber isomorphisms. And so recall what is a map of this bijection. So if you have this say if you have this two cell, then you can factorize this two cell through the standard natural two cell phi, and you will have this map, and this map is X. So this X fits into this diagram. Okay. Yeah, but in general we have the same situation. So you just should factorize this diagram through natural two cell, and you will have this angled alpha. So okay, this is just from the construction, from the general construction. Now, suppose that we are given the following cospan, then the comma infinity category is left representable. If there exists such map L that you have this isomorphism. So it means that this something is representable. So this comma object is represented by this L. And right representable in the case when there exists R such that you have the following dual isomorphism. Okay. So the construction of infinity category, comma infinity category is useful, recall, for standing independence, so some independence, and the crucial thing here is the fact that this comma infinity, so this home object in infinity category is right representable if and only if this G admits an absolute right Lifton along F, so you have the following absolute right Lifton diagram. So there is some relationship between the notion of absolute right Lifton diagrams and the notion of home objects in infinity category. And our goal is to prove to establish this equivalence of this. Okay, this equivalence. Okay, and now to do this, we should consider 3 stages. So just three theorems, but so the first one tells us that it characterizes those diagrams that define absolute right Lifton diagrams between comma infinity categories. And it said that this diagram is absolute right Lifton diagram if and only if you have the following isomorphism. So we see that we can translate the fact being right Lifton diagram into the fact of being isomorphic between some home objects. So it means that you have a notion which that doesn't depend on the model. So it is a basic it is a basis for the model independence. Okay, the next result tells us that we can omit a natural transformation in the condition, and it means that you just have some diagram without any row, any to cell, and we can omit it and and the next and the last stage is about that is about a criterion to construct a right representation to this to some concrete to any concrete home objects. So if you have some home objects, you can give an appropriate representable an appropriate object which represents this home object. So we in this case we have no a priori specifying functor R, so we can construct this one from the home object. So and of course each so from the first theorem, the sect will be follow will follow, and the second one implies the third one, but we will prove only the first one. So since the corresponding proofs are similar in some sense, but technical, and I think that you can read it in really real book, Rails book. So now the first theorem. So suppose that we are given the following diagram with this natural transformation rho and this commutative diagram, commutative triangle. Then this diagram is an absolute right Lifton diagram if and only if we have the following isomorphism between home objects. So recall that it means that we replace in mind this one by ID identity on B, and so it means that if and only if each home object between F and G is representable by this R. So it means that you have the following factorization. So so take this diagram and consider the question with the natural two-cell phi, and this Paston diagram can be factorized in the following way. So you have some y between this cone and the standard cone from the natural two-cell, and yeah, so yeah, and this factorization will be used in the proof. Okay, so let's prove this theorem. So suppose that this R rho defines an absolute right Lifton of G through F, meaning that you have the following diagram, which is an absolute right Lifton diagram. So recall that the notion of being an absolute right Lifton diagrams mean that you have the following universal property. So if you yeah, if you have some diagram, some square diagram between four objects, say X, C, B, and A, then you can factorize it through this canonical two cell. So in particular case, you have a factorization like this, and in this case we factorize this this diagram through the no, it's not the case, but okay. So any the diagram with X here and without this guy can be factorized through this two cell, meaning that you have some equality between the composition of two cells. So you will be you will have some two cell here and some two cell here, and the composite will be the original one. So yeah, this is some I just recall some definitions. So the definition of absolute right Lipton diagram. So suppose that you have this diagram, this triangle diagram, and this is an absolute right Lipton of G through F. Then yeah. So we have the definition here. So yeah, any diagram like this can be factorized through this lambda, where lambda fits into the absolute right Lipton diagram. Okay, and we can apply this property, this universal property, to the comma colon and the home object between F and G. So consider the following diagram and just factorize it through rho. Then you get this zeta, and there's more. You can use the one cell induction. You can apply it to this zeta, so you can factorize this zeta as the following Whiskeron into the following Whiskeron. So this Whiskeron with z and this phi, Whiskeron through phi, and then you can substitute the equality from the following equality. You can substitute it into diagram. Okay, and then you will have the following diagram. So just okay, yeah. Here we have phi, and we just factorize this. So I replace this guy by this guy. Okay. So now consider the composition YZ, the following composition. These composition factors the comma colon. The factors the comma colon for comma object FG through itself. You see that you have a factorization of this home object FG. So it means that you know that this factorization is unique up to fibered isomorphism, and then it means that this YZ is fibered isomorphic to identity on home objects between F and G. So it means that we should only prove that the reversed or composite is also isomorphic to identity morphism. In that case, we just we will move backward, and we will start with this diagram, and so in this case I changed the order between Y and Z, and I just use the properties which was used before in the reversed order. And in this case, you will have that the composite phi zy is phi over rho, but also from the weak universal property, it follows that you have that the following equality. So zy equals identity map on home object between B and R, and thus we have an isomorphism between these home objects, and it means that this home object between F and G is representable by R. So the direction, suppose that this functor Y, which was constructed earlier, so recall that this functor Y is here. So it is derived from the decomposition of this two cell, and we suppose now that this Y is a fibered equivalence over C cross B, and we will prove that R rho is an absolute right lifting of G through F, and to do so we use first of all an uniqueness property of comma infinity categories. So the natural transformation, this natural transformation from the conditions of the theorem, and here are the weak universal properties of comma cone from this home object, but we know that if something fits has some universal properties, the universal properties which are derived from the home comma categories, it means that this object is well defined up to isomorphism, up to fibered isomorphism, and so we use this idea here, and we can obtain the desired result. Okay, now let's discuss the following corollary. Consider the condition. So you have some functor F between infinity categories, and this and the property of this functor being fully faithful is equivalent to each of these items. So the first item said that you have the following triangle, an absolute right to left lifting diagram, and another one means that for any infinity category X, the induced functor between homotopy categories is fully a faithful functor of one categories. And the last one, so it is the following, that you have the following induced. So the following induced map is the identity to cell. Is that identity to cell? So so this this diagram corresponds to this one, and so recall that F is a map between A and B, and you know that there is a bijection modular isomorphism classes, isomorphic classes, and this diagram corresponds to this one, and this arrow is derived from this identity to cell. So and the statement is that this is a isomorphism. This is isomorphism. So these items are equivalent to each other, and they are equivalent the condition that the functor F between infinity categories is fully faithful. So the proof is obvious. So note that the first and the second items are equivalent with the third one. So each of these notions are equivalent with the third one. So this is an easy. That's easy. This is an. It follows from the definition of absolute right-left lifting diagrams, and the equivalence between and the fact that these diagrams, these triangle diagrams, are equivalent with the fourth one follows from the previous theorem. So it follows from the previous theorem, just in the case that you have R here to be an identity morphism, and it follows the equivalence between this item. Another corollary that cosmological functors preserve absolute lifting diagrams. So it's easily follows because we can characterize this property of being absolute left. An absolute lifting diagram. We can characterize this property as being just in terms of common infinity categories, but the last one is of course preserved by cosmological functors. So I will recall the notion of cosmological functors, but you can think about it as just usual functors, and you just apply this functor from to each element of the diagram. Yeah. So let F be an cosmological functor. So together with the following Wright-Lifton diagram, then it induces a fibrate equivalence, and we can apply this this functor F to this fibrate equivalence, and use the fact that F preserves pullbacks. So you know that these guys are pullbacks, and cosmological functors should preserve pullbacks. And moreover, F preserves the notion of being a weak equivalent. F preserves weak equivalences, and in this case, you have the following equivalence. So you can just apply F in this way, and in this case, you should prove the universal property of this diagram, but probably it's not easy to do. It's not easy to do, but by means of this notion of comma category, it's natural and it's easy to derive. Yeah. Okay, and yeah. Now. Okay. Mm-hmm. Just a second. Yeah. So we have the following isomorphism, and in this case, yeah, this is obvious, and so it is explained more in details here. So you can apply F into this to this diagram, and you can factorize it by means of this isomorphism, and it means that in the category L you will have the following absolute Wright-Lifton diagram. So okay, the rest is obvious, but I decided to write it down. Okay. Now the second theorem in the second theorem said that suppose that we're given a trio of these functors R, F, and G, and in this case, you will have the following bijection. So of course, I mean that here I mean that that we probably consider isomorphism classes here, but yeah. So we now we no. So now we suppose that these diagrams are probably the diagram like this is not right Lifton diagram, and but some diagrams, some to cell, you have some to cell row, and some computed diagram. And in this case, you will have this bijection. And how does it work? So suppose that you have this to cell, then you can compose it with the following phi and natural to cell phi, and factorize it in the standard way, and you will have this y. So this is a standard map. Moreover, if rho is an absolute right Lifton of G through F, then y is an equivalence. So if y is an equivalence, then I should write this factorization. Okay. Yeah. So in this case, we have the statement of the previous theorem, but that's the more general statement is also true. So you have the following bijection without rho being right Lifton diagram, being the appropriate to cell of an absolute right Lifton diagram. Okay, and so I skip the proof and consider the corollary. So suppose that you have this parallel pair of morphisms between A and B, then there are bijections. These two bijections. On the left hand side, you have and on the right hand side you have something similar, but consider the top of these diagrams, the tops, and they're different, and so you can replace this home object by this, and equivalently you have a bijection with these two cells between these parallel arrows, and these bijections are constructed by passing with the left, right, comma, column over G or F respectively. So consider, for example, the correspondence between on the left. So on the left we have the following situation. So we have these two cells, and we can pass it with the following standard to cell, and in this case we will have a factorization. So the standard way and this case and these are differed by these objects. So it's pretty natural and obvious. So the next theorem allows us to recognize when a comma infinity category is right representable in the absence of predetermined representative functor. So now we suppose that we have a cospan like this, and you can form, of course, this home object between f and g, and this is right representable if and only if there exists such a right adjoint right inverse. So look at this diagram here, and yeah, you have this home object and this trivial maps, or this standard maps P0 and P1 projections, and the question is about the existence of such I. So this home object is right representable if and only if there exists such an I that this is a right adjoint to the functor P1, and the second condition is that it is right inverse in a sense that the co-unit map is an isomorphism. So recall that co-unit map means that you should consider the composition between in such an order. So and this should be an isomorphism with it should be an isomorphism. So it's isomorphic to identity map on C. Yeah. Okay. So we have the following theorem, and moreover, this composite P0I, this composite defines the representing functor. So you have the following triangle diagram here. So this is a usual cospan, which we have from the conditions, and then the map from C to B is by 0I, and the natural 2 cell is induced by the functor I from C to home FG. So we can reconstruct the data of this right Lifton diagram, and yeah, this is a general case of the result. So consider the following example. So what is an application of these results? It turns out that we can apply this technique to the case of an adjunction, and to the case of constructing limits, and so on. But in this seminar, we will restrict. We consider only these cases. So the case of adjunctions and the case of limits. Yeah. Suppose that we are given the following adjunction, then we know that this. Then we should verify that this junction translates to the following isomorphism of comma objects. So, but it is straightforward from the previous theorem. So we know that the notion of adjunction can be encoded by the right or left Lifton diagrams. So you have the following right listing diagram, and epsilon here is co-unit, also, yeah, and in this case, so we know that this diagram is an absolute right listing diagram if and only if we have the following isomorphism. And replace appropriate variables, appropriate maps, we have replacing these maps, we have the following isomorphism. So yeah, BR here is a BU, just here B and BR, BU, and here FG. So FG just identity on A and F. Yeah, and so by this notation we have the following equality. Okay, and we are done. So the next example. So suppose that we have this adjunction, and also we have these generalized elements. So elements in a sense of Laver or something like that. So some generalized elements, and then we should have the following isomorphism. But it's an easy exercise. From the previous example, it follows straightforward easily. Yeah, recall that fibered equivalences can be pulled back, and consider the following pullback. So by this map consisting of AB, the pullback along this map, and in this case we will get this comma object from A to UB, and also we have the following isomorphism, so yeah, well, this isomorphism encodes the fact that we have an adjunction, and this diagram is also pullback. And this pullback will be FB over A, but from this property we have that these guys are equivalent, are isomorphic. Okay, now let's talk about adjunctions, limits and colimits via commas. So we have discussed the case of adjunctions, and now discuss the case of limits and colimits. Yeah. So recall the definition of the infinity category of cons. So given a G index diagram, so this is an object in the category of diagrams of form J. So J index diagrams in an infinity category A. Then we can define the following infinity category of cons as just the category consisting of just the following category. So home over AJ between diagonal functor and D. So recall the diagonal functor can be constructed from the terminal functor and the canonical bifunctor or functor of cotensor product in some sense, which constructs this, this functor gives us from this pair GA the following object AG, and applying this bifunctor to this terminal functor, we get the following constant diagonal functor, and so from the construction of infinity infinity category, we have the following two cells. Okay, and the consequence from the first theorem will be the following proposition. So the map L, so the generalized object L in infinity category A defines a limit for a diagram D if and only if there exists a fibered equivalence like this. So recall that we know the definition of the notion of limits in terms of left, right, left lifting, absolute left lifting diagram, but also we can convert this definition via the following comma infinity categorical notion. So let's prove this result. So recall, I've said before that lim D is the limit of a diagram if and only if you have the following. You have the following left lifting, absolute left lifting diagram. Right lifting property. Left stands for colimits. Okay, and applying the result, the main result. So just the first theorem. I think it will be surface, but okay. And the result from the result of the first theorem implies that we will have the following fibered equivalence. Okay. Now, also limits and colimits represent cones. So a family of diagrams D admits a limit if and only if this comma category is right representable. So we saw in this case that this the condition of existence this limit for this single diagram means that we have the following representation. So this home object is representable by this object L over A. But in general case, in this case we have the similar isomorphism. So you can just say that this home object is representable by this L. So And this L, of course, defines the limit functor, and dually for the colimit case, the existence of this colimit of generalized generalized diagram is equivalent to the fact that this com is left, not right, but left represent. Okay. Well, the following proposition says that limits are terminal points. So you can characterize this property, the property of limits, and you can give another definition of limits and colimits, just as in usual case. So you can say that diagram D in infinity category A admits a limit if and only if this infinity category admits a terminal element, and admits a colimit if this infinity category admits an initial element. That's fun. That's cool. Okay. But I skip the proof. It's easier, but probably it's quite technical, and it's not interesting, in my opinion. So okay, now we can say a few words about model independence or basic infinity category theory. Yeah, just I said before, any categorical property that can be captured by the existence of fiber equivalence between common infinity categories is model independent. So it means that if you can characterize something via this common infinity notion, then you get model independent some model independent notion. Yeah, model independent means that the property is preserved by any cosmological functor, and reflected by those that define weak equivalences of infinity cosmoi. Now I recall the definition of a cosmological functor. I should do it before, but I decided to do it now. But okay, anyway, a cosmological functor is a simplicial functor between an infinity cosmoi that preserves the class of isofibrations, internal object one, and also cotensors like this. So U is some simplicial set. A is an object of infinity cosmos K. Also, it follows that it preserves weak equivalences and trivial fibrations. It follows from the definition. And also cosmological functor F induces two functor between homotopy categories. Okay. Now, suppose that F between K and L is some cosmological functor, and in this case, it induces the functor F2 between homotopical categories of K and L. And this functor F2 will preserve adjunctions, equivalences, isofibrations, trivial fibrations, groupoidal objects, products, and comma objects. It is easily it follows easily from the definitions. But anyway, any two functor preserves adjunctions and equivalences. The first fact. The second, isofibration are preserved by the definition of cosmological functors, isofibrations. Also, trivial fibrations is the class which is just an intersection between isofibrations and equivalences. So both of them preserved, and it means that trivial fibrations are preserved as well. Also, E is groupoidal if and only if the induced map, the induced isofibration is trivial isofibration. These facts prove the following proposition. This proposition. Okay, but recall that groupoidal objects can be characterized in an infinity cosmos in different ways. So the first way is to say that E is groupoidal, of course. The second way, that for any two cell with codomain E is invertible in K2, any two cell with codomain E is invertible in a homotopic category of K. The third one is that for any X, for any objects of infinity cosmos, this home object is a Kan complex. And the last one, that this isofibration is an trivial fibration. So, and recall how to prove the equivalence of these conditions. So from the first condition follows the second one, obviously by definition. So if E is groupoidal, then any two cell is an invertible. It's easy. The equivalence between the second one and the third one, this is a theorem by Joyal, that two cell invertible and this home object is a Kan complex. So the condition number 4 is equivalent to say that this map is a trivial fibration for any X. But since it is a trivial fibration, we have the following fact, that for any one simplex in this home object, any one simplex is an isomorphism, and thus we have the third condition. So the third condition implies the first one, just from the fact that this inclusion is a weak homotopic equivalence. Yeah, okay. And the preservation of commas follows from the definition of commas. of course, and by uniqueness of commerce modular for fibered isomorphisms. So the next definition is about weak equivalences of infinity cosmoi. So we say that f a functor between some f is some cosmological functor is a weak equivalence when it is surjective on objects up to equivalences and a local equivalence of quasi-categories. So the first condition means that for any object X, there exists an object A such that we have an isomorphism in the category L, and the second one means that we have this local equivalence condition. So we have an equivalence between these quasi-categories for any objects A and B from infinity cosmos K. And the last proposition is the statement of is the main result of our seminar. And if f is a weak equivalence of infinity cosmoi, then the homotopy functor, the induced homotopy functor f2, defines by equivalence f2. So by being by equivalence mean that f2 is surjective on objects, and you have the following local isomorphism property. The second one, that f2 induces the following isomorphism by adjunctions, on isomorphism classes of objects. The third one, that f2 preserves and reflects groupoidal objects. So A is groupoidal if and only if fa is so, and also f2 preserves and reflects equivalences, and f2 preserves and reflects comma objects. Sorry, this is not the main result, but the next will be so. Of course, this fact is also trivial. In some sense. It follows from the definition, from the definitions easily. So, but the next theorem is about model independence of basic category theory. So the fact of being adjoint, so the adjointness, the existence of left and right adjoint to some functor, the question of whether a given element defines limit or colimit for a diagram, and the existence of a limit or colimit for G-index diagram. These are model independent notions, model independent conditions, and of course we have proved these results, of course, by the previous theorems, and we know that the adjointness fact is encoded by comma stuff, and the others are also encoded by this technique, and it means that we are done. So this is an example of an application of this notion, and But of course it is not. Yeah, it is some illustration, but there are a lot of interesting things here, and but I think that I can stop here. And thank you for listening.
All right, thank you, Misha, for yet another wonderful talk. If there are any questions, please ask them now.